Okay, this is a short video on solving linear equations. On your Unit 0 test, you were asked to solve this equation for x. Cx plus a is equal to b minus dx. And when encountering an equation like this, the first thing you should do is try to recognize the terms that have x in it. So these two terms, the cx and the negative dx, both have x. And you should also recognize the terms that don't have x, obviously the a and the b. The method of solving these equations is to get all the terms that have the x to one side. So we'll leave the cx here. We'll move the minus dx to the left side of the equation, makes it positive dx. And then we'll move all the terms that don't have x to the right side. The b stays there. And of course, the a would be subtracted, and you would have this. The second step in solving these types of equations is to isolate the x. Notice that cx and dx are not like terms. You can't combine them easily. But we can factor. We can factor out the x and write it this way, c plus d times x. And again, just double check. You notice that you do have cx plus dx. Okay, so factoring out the x, we have c plus d times x is equal to b minus a. And the final step to the solution is simply to divide both sides by c plus d, right? C plus d. And obviously this factor would cancel, c plus d. And so your final answer should have been x is equal to b minus a over c plus d. Okay, fairly straightforward method of solving linear equations. The three steps you're thinking is you move all the terms that have what you're looking for to one side. You factor out the thing that you're solving for, in this case the x, and the third step would be to divide by the coefficient of what you're looking for. In this case, we divided by c plus d. Okay, let me show you a couple of equations that sort of fit this pattern. Here's a fairly simple equation. It says solve for x. We know there's an x here and there's an x here. We're going to move all those x's to one side. So we have x minus cx and a plus b. And then we factor out the x. I'll factor it out the back. You can factor it out the front if you want, but I'll factor it out the back. Make sure you factor it correctly. There's your 1x. There's your minus cx. So we have 1 minus cx is equal to a plus b. And lastly, we can divide x is going to be a plus b over 1 minus c. And that's the solution. Now, where would this come into play later down the road? Here's an equation that comes out of calculus. You have done an operation. You've actually differentiated implicitly, not that you need to know how to do that. But you've gotten to this line, and the task is to get the dy dx by itself. Solve for dy dx. Now, even if you don't have any clue what dy dx means, you notice there's that expression here, and there's a term that does not have it. There's another term that does not have it, but this term does have it. Aha. So we're going to move both of those terms to the same side. We have dy dx that was already there. We're going to move this term across, minus x dy dx. And that's going to be equal to 3x squared plus y. Lastly, we factor, or not lastly, next we factor out the dy dx. I'll factor it out the back. Notice this is very similar to what we just did. And 3x squared plus y. And lastly, and again, on this factoring step, if you're unsure, you can always double check and make sure, sure enough, there's your dy dx, that's this, and there's your minus x dy dx, that's this. Okay, so our final step is to divide dy dx is equal to 3x squared plus y over 1 minus x, and you're finished. Here's another problem of the same ilk. This is also found in calculus. We've done a process called integration by parts, and we've arrived at this very confusing looking equation here, and the task is to solve for this expression. Now, you don't know what that means. This is a pre-calculus class. This, in fact, is the integral of e to the x cosine x dx. But even if you have no clue what that means, the pattern of solution is just like what we've done. Here's that thing that you're trying to get by itself. This term does not have it. This term does not have it, but this term does. In fact, it's exactly what we're looking for. Okay, so we're going to move the two terms that have this expression to the same side, and we can do that pretty easily. Okay, so we have the integral of e to the x cosine of x dx, and we're going to move this one across. Well, it is minus, so we'll add the integral of e to the x cosine of x dx. And on the right side, we have these two terms. They just stay there, e to the x sine x and e to the x cosine x. Now, how about the left? Well, golly, this looks like two of exactly the same things. It's a plus a, two of them, two a's, right? So we have this expression. We have it added to itself, so that gives us two of those things, two of these guys. Now again, you don't have to know what this means. I've left off an x here. 2 e to the x cosine x dx. You have two of them. It equals e to the x sine x plus e to the x cosine of x, right? And then lastly, we would divide. Notice that this is factored. We have 2 times, so we simply divide both sides by 2. So the integral of e to the x cosine of x dx is equal to all of this e to the x sine x plus e to the x cosine of x divided by 2. Or if you want, you could write it as 1/2, right? Dividing by 2 is the same as multiplying by 1/2. Okay, so this course is obviously not dealing with calculus, but it is dealing with algebra and being able to solve linear equations. So if we go all the way back to what we had to begin with, here was the linear equation that you had on your Unit 1 test. You know how to solve it by moving, factoring, dividing. This was a similar type of problem, right? Move, factor, divide. Here was one that was an application of implicit differentiation, but again, move, factor, divide. And lastly, an application from integration by parts, move, factor, divide. The fact that you have no clue what this means has nothing to do with the method of solution. So if I pop up a new equation, and I'll just make one up here. If I have 3 times the hyperbolic cosine of theta is equal to 2 theta minus theta times the hyperbolic cosine of theta. And I say, I want you to solve for this expression, the hyperbolic cosine of theta. And you say, well, golly, I don't know what that means. Doesn't matter. This is what we're trying to get. If you're unsure and you don't know how to proceed, you might want to say, well, let me just replace this thing with the letter u for ugly. So then you have 3u is equal to 2 theta minus theta u. And now we're going to solve for u. Solve for the ugly thing. And again, it's just move, factor, divide. This term has a u in it. This term has a u in it, so we'll move them to the same side. So we have 3u plus theta u. That's a u there, Joe. 3u plus theta u is equal to 2 theta. And then we're going to factor out the u. That's what we're looking for. 3 plus theta is equal to 2 theta. And then we're going to divide. So u is 2 theta over 3 plus theta. Now, even if you're not, sure what happened there, the process, move, this was the move step. The factor step was here, and the divide step was here. Okay, so sure enough, this hyperbolic cosine of theta can be 2 theta over 3 plus theta. And it might be interesting to actually solve that on the calculator. We might do that later. Notice that hyperbolic cosines are not in this course. They're actually not even in calculus, not the AP calculus, but you might see it down the road. The hyperbolic cosine function, by the way, is the function that gives the graph of a hanging cable. So when you hang a cable between 2 points, it does not assume a parabolic shape, but it assumes a catenary, which is a hyperbolic cosine. Okay, so let me go ahead and stop this little video now on solving linear equations.